So have you ever actually stopped to wonder how an artificial intelligence remembers things? It's a pretty fascinating mystery. I mean, when we think about memory, our minds usually go straight to things like filing cabinets, databases, or a traditional hard drive that neatly organizes everything into little folders. But large language models, or LLMs, they don't work like that at all. There's no secret internal hard drive packed with PDFs or Wikipedia articles in there. Yet somehow, they seem to know practically everything. So welcome to this explainer. Today, we're going to completely demystify AI memory and uncover the hidden architecture of how machines actually store knowledge. And that brings us to the core question we need to answer today. Where exactly is all that data hiding? Think about it. If you ask an LLM, hey, what is BGP? It spits out a perfect definition. Ask it to explain the messy details of a TCP three-way handshake, and you get an answer instantly. It might even know the exact CLI command to configure some highly specific feature on a Juniper MX960 router. So, if it hasn't saved a bunch of networking textbooks and manuals on a hard drive somewhere, how on earth is it retrieving these highly specific technical facts? Well, the answer is going to completely redefine how you think about information storage. To answer that, here's our roadmap for today. Number 1, AI doesn't use folders. 2, parameters and weights. 3, the concept map. 4, generating answers. 5, AI hallucinations. And finally, 6, RAG and network AI ops. All right, let's jump right into section 1. AI doesn't use folders. Okay, so let's dive into this. To truly understand AI memory, we kind of have to unlearn everything we know about how traditional computers store information. Normally, if you want to document on routing protocols, you go to a directory, you open a PDF or a Word doc, and you read the exact text sitting at a specific file path. But an LLM, once it finishes its training process, it tosses out those source documents. It doesn't keep them. Instead, what's left behind is this massive ocean of decimal numbers. We're talking billions, literally hundreds of billions of them. And they're just simple decimals, like 0.128 or negative 0.734. The AI's knowledge doesn't exist as readable articles anymore. It exists as these dispersed mathematical relationships encoded across all those numbers. Honestly, that is the most crucial concept to wrap your head around today. Moving right along to section 2, unpacking parameters and weights. So you're probably wondering, what exactly are all these billions of decimal numbers? Let's unpack the actual jargon the data scientists use. The overarching term for all these learnable numerical values is parameters. Think of parameters as the dials and knobs of the AI. Now, a super important subset of these parameters are called weights. Inside a neural network, as data flows from one artificial neuron to the next, the weight determines just how much influence that specific piece of input has on the next step. So the big takeaway here is that weights are a primary type of parameter. They aren't separate little warehouses of knowledge. They are literally the fabric of the network itself, constantly adjusting during training to encode statistical rules. But there's another really vital piece to this puzzle: embeddings. See, when you type text into an AI, it first chops it up into chunks called tokens and assigns them an ID number. Let's say the token for BGP gets the ID 9123. Well, the number 9123 has absolutely no actual meaning on its own, right? That's where embeddings come in. The model uses embedding parameters to map that token to a high-dimensional vector. Basically, it gives it a coordinate in mathematical space, something like 0.12, negative 0.43, 0.81, 0.27. This gives the concept an actual mathematical location within the AI's brain, which perfectly sets up section 3, embeddings and the concept map. Let's zoom out for a second and look at how these vector coordinates actually behave, because it creates something truly wild. I want you to imagine a massive multidimensional 3D concept map. Because of those vector coordinates, concepts that are contextually related physically cluster together in this mathematical space. So that coordinate we made for BGP, it doesn't just sit there in isolation. It floats very close to other terms like routing, router, network, MPLS, TCP, and connection. The AI hasn't memorized the sentence, BGP is a routing protocol. Actually, scratch that. It hasn't memorized sentences at all. Instead, through training, it's formed these incredibly strong spatial and statistical relationships between clustered concepts. The knowledge is entirely structural. Section 4, how AI generates answers. Okay, so we've got this vast landscape of parameters, weights, and concept clusters. Let's trace the exact steps of how the AI actually uses all that to talk back to you. Say you type in a question like, what is BGP? First, your text input undergoes tokenization, turning words into token IDs. Next up, those IDs are mapped to their embeddings, fetching their exact coordinates from our giant concept map. Then it passes through the transformer architecture and attention mechanisms. This is where it performs massive, heavy-lifting matrix operations using all those billions of parameters we talked about. Finally, the model outputs a probability distribution. Basically, it literally calculates the statistical likelihood of what the very next word should be. It might predict that the next word is BGP, then it recalculates to predict is, then A, then routing, and so on. It is generating the answer one single token at a time, based purely on math. And honestly, this brilliantly illustrates a really profound parallel. Think about how you and I learn. If you read 100 textbooks on network engineering, you don't have 100 PDFs saved in your brain. You can't just close your eyes and say, oh yes, the answer is on page 127 of book 38, paragraph 3. No way. Instead, you extract the concepts, you build experience, and you form mental relationships like knowing that OSPF is an interior gateway protocol. You build a web of knowledge. While an LLM is purely mathematical and obviously not biological, it operates on a remarkably similar principle. It retains the patterns and relationships of the data it read, not the raw files themselves.
All right, Section 5, the cause of AI hallucinations.
But listen, this method of generating answers purely by predicting the next probable word, it has a well-known, glaring vulnerability. Let's address the elephant in the room. Because the AI doesn't have a literal database of hard facts to look up, it is entirely reliant on generating a plausible-sounding sequence of tokens. And this is exactly what leads to AI hallucinations. If you ask it for some highly obscure or completely made-up Juniper CLI command, it won't necessarily just say, I don't know. Instead, using its structural knowledge of what Juniper commands generally look like, it might confidently invent a command starting with set protocols, followed by complete gibberish that just looks shockingly authentic. It's trying its best to give you a mathematically highly probable sentence, but it's not bound to absolute real-world truth.
Finally, Section 6, RAG and Network AI Ops. Now, in an enterprise IT environment where guessing a wrong command can literally take down an entire network, hallucinations are an absolute deal breaker. The ultimate solution to this is RAG, or Retrieval Augmented Generation. We can perfectly contrast the two types of knowledge to see why this is a game changer. Training knowledge is what we've been discussing. It's encoded permanently in the model's parameters. It's super fast, but nearly impossible to update without expensive retraining. If a new software version drops tomorrow, the model's out of luck. RAG knowledge, on the other hand, lives in an external, easily updatable knowledge base. When you ask a question, the system first retrieves the relevant factual documents, like your actual official network SOPs, feeds that context directly to the LLM, and forces the model to base its token predictions only on those hard facts.
This right here is the true superpower for something like network AI ops. The foundational LLM understands the general concepts of networking from its parameters, sure. But what is happening right now on your specific network of 23,000 routers? The LLM has absolutely no idea. But by hooking the LLM up to live data sources via RAG and APIs, pulling in real-time SNMP telemetry, syslog errors, live topology changes, interface traffic, and current BGP states, we essentially merge the AI's structural understanding of networking with the absolute real-time facts of your environment. It can actively read the real situation on the ground before it ever generates an answer. Which leaves us with a truly fascinating question to ponder. If an AI is, at its absolute most fundamental level, just predicting the next token based on math and external documents, how is it capable of looking at a downed BGP session, analyzing the interface states, and correctly deducing the root cause of the failure? Is this step-by-step analysis genuine reasoning, or is it merely the illusion of intelligence created by highly probable token sequences? That exact distinction between prediction and actual cognition is what we'll be breaking down in our next explainer. You definitely won't want to miss it.